So let us talk about an interesting set of properties. Let's define two kinds of strategies: active strategy and equalizing strategy. So the active strategy is very simple. So a pure strategy, I emphasize, strategy is called active if there exists a max-min strategy, in general not pure, such that this Si is in the support of that max-min. So that Si has a positive probability. So an active strategy is a strategy that appears in the support of some max-min strategy. Another definition is of an equalizing strategy, and please note that's not a universal definition. At least one other, maybe even two other books, at least one or two books I've seen, at least a book by Machler, Solan, and Zamir, they use another definition of equalizing strategy. So that's the definition I use, following again Holzman's lectures. So that's the definition which will be relevant to our course, but in the books it can be different. So please notice that definition of an equalizing strategy is not universal. So a pure strategy is called equalizing if I assume j is not equal to I, that's the notation, for every max-min strategy pj star, that Si, that pure strategy, gives to player I the best possible against that player. So we know that if player I plays max-min and the other player plays her max-min, then player I gets exactly the best possible. But in this definition, we are talking about a pure strategy that gives the best possible against only against all those strategies which are max-min. It can be that it does not always give the best possible. It can be that it only gives the best possible against that strategy. So let us look at an example. So this is a simple example of a coordination game. So we have two pure Nash equilibria, AC and BD. Yeah? This and this. And we also have one other which is fully mixed, which is half-half. So in this case, let us find this half-half. So it's a nice exercise. So why is it half-half? Because that's weird. I think I again have confused this. It's a zero-sum game. Because basically, 1 second. So, okay, I did mean this to be a zero-sum game, and I just wrote this not exactly how I wanted. So that's the game. That's the zero-sum game. So it's not a coordination game. At AC there is 1 and -1, and B and BD there is 1 and -1, and at the other profiles you have 0, 0. So here we have only one Nash equilibrium, which is half-half, and this is how we get it. So that we say that what is the max-min, because that's a zero-sum game. And how do we look for max-min? As before. So we say, okay, what does player 1, does the raw player get when the second player plays C? It gets 1 times P. P is the probability with which player 1 plays A. Plus 0 times 1 minus P. So it gets P. Again, strategy C. On the other hand, when the second player plays D, player 1 gets 0 times P plus 1 times 1 minus p, so it gets 1 minus p. So against d, it gets 1 minus p. And the worst possible that the second player, the column player, can inflict upon player 1 is therefore this hedge denoted in the purple color. Therefore, the best possible that player 1 can do against this purple hedge is playing this intersection. So what is the intersection? It's exactly when p equals to 1 minus p. That's when p equals to half. And symmetrically we can get the q equals to half, so the only mixed Nash equilibrium is half-half. Now that means, and let's go back to the definition, that now I hope you will understand these definitions better, so that pure strategy is active if there is some, at least one, max-min where it's in the support. So here both strategies are, of both players are in the support, so every strategy is active. Now what happens with being equalizing? Here you are an equalizing strategy if you provide to your player the value of the max-min, provided that the other player plays her max-min. So you're not always promised to provide max-min, but if the other player plays her max-min, then you give your max-min, you give the value of the game, in other words, the value of the game, of the mixed game, but you have to play a pure strategy. And here again, when both players, imagine that one of the players playing her max-min, which means, as we said, randomizing half-half. Then playing any pure strategy against that would provide you the best thing you can have. But it's not, definitely it's not something which is an optimal thing for you. It's not a max-min for you, because it's not the best thing you can get against the worst behavior. But it's an equalizing strategy, because it provides the best given that the other person plays her max-min. So in this case, both strategies are equalizing and both strategies are active. Okay. Now let us mention an important observation, that a max-min strategy that happens to be pure has to be active and has to be equalizing. Please notice that does not cover the previous example, because in the previous example both max-min strategies, they were unique and they were not pure, they were fully mixed. So that's not the case, but in general, if a max-min strategy, there is a max-min strategy which is pure, it's both active and equalizing, because it's active by definition of being active, because it's in particular in the support of a max-min strategy. It's also equalizing because we assume it's a max-min, so it in particular provides your optimum against everything, in particular against the other max-min. So that's interesting, and let us go further. Now let us prove an important proposition which just is simple, but it helps us solve some examples simpler. And that says that each active strategy is equalizing. By the way, the converse is also true, but we are not going to prove it now. Maybe later. So each active strategy is equalizing. So I will give two proofs. I hope it will also help you to get a bit used in this in these definitions. So one proof is as follows. Fix an active strategy. By definition, it means that Si, this active strategy, belongs to the support of some max minimizer of player I. Now, as we have proven for zero-sum games, for each max minimizer of player I and max minimizer for P star of player I and max minimize the Q star of player J, another player, the other player, in the mixed extension. P and Q, P star and Q star, they constitute a mixed Nash equilibrium. And well, mix max min of the first player is equal to min max of the second player. I meant to say, of course, of the max min of the second player. Now, by the lemma, so please let us see the chain of the arguments. Lemma says that each strategy in the support of a Nash equilibrium, of a mixed Nash equilibrium, is the best response to the strategy of the other player. Now, but we begin with the fact that Si belongs to the support of some max minimizer. Now, this max minimizer constitutes Nash equilibrium with any max minimizer of the other player. P star constitutes a Nash equilibrium with any Q star. Therefore, by the lemma, each strategy in the support of P star, in particular this Si, is the best response to Q star. Because P star Q star is a mixed Nash equilibrium. Therefore, Si is the best response to Q star. And since this holds for any Q star, which is a max minimizer of player J, then we can say that Si, we have proven that Si is the best response to any max minimizer of player J. And by definition, that means that Si is equalizing. Another proof, and that's the proof by Ron Holtman from his lectures at least, of the same simple statement, is actually it less leans on the theorems and propositions we have proven, but more on the definition. So that's actually a nice exercise to practice definition. So we need to prove that every active strategy is equalizing. So without loss of generality, assume that we are talking about a strategy Si of player 1. We need to assume that there is strategies Si of player I. Now assume that there is a strategy, let's call her Sk, which is active but not equalizing. What does it mean? By definition, active means that there exists a maximum strategy P that has a positive kth element. Now, what does it mean that it's not equalizing? Not equalizing means that there exists a maximum strategy Q of player 2 such that the value that player I1 gets from playing Sk against Q is smaller than the value of the game. The value of the game, I remember, is the common delta that both get and they both play their optimum strategy. Now let us calculate what is this value when player 1 plays P and player 2 plays Q, when they both play their max min. That is by definition of a mixed extension. A combination I goes from 1 to m of Pi times U1 of Si and Q. Now, since Q is optimum, then U1 against Q is at most V star, at most a value for any I. Now, by our assumption, when player 1 plays Sk, U1 is strictly smaller than the value. Another assumption is that the weight of Sk, Pk is strictly positive. So this is a sum of this is a convex combination of ui's, such that each one of them is at most v star, and there is at least one element which is strictly smaller than v star, and it has a positive weight. So therefore, u1 pq of p in q is strictly smaller than what would have happened if we summed simply v stars, which would be v star. So it's simply smaller than the value, but it's contradictory to the optimality of p. So basically, the intuition is that, not the intuition, the proof says that, okay, being active, it means that you have a positive weight in some strategy. Being equalizing, it means that there is an optimum strategy of another player, such that against that optimum strategy, being non-equalizing, it means that there exists an optimum strategy of another player, such that you are suboptimum against that, you get less than value against that optimum strategy. And so you get less than value, and the weight of that is positive, and therefore the value of player 1 and player P and Q is strictly smaller than the value of the game, which is contradictory. Now, we are going to use this statement that each active strategy is equalizing when in both directions. So sometimes we are going to say that there is a strategy which is active, it's in the support of a Nash equilibrium, a max-min strategy, and therefore it has to be equalizing. Sometimes we are going to use the contrapositive. We are going to see that something is not equalizing and prove that it's not active. But we are going to use that to solve game, in the sense that to find all the mixed Nash equilibria. And we are going now to see an example of such a game. So that's kind of another tool, this statement which we've just proven. And now we're going to exemplify this tool on again, an example from Holtzmann's lectures. So imagine two players. Player 1 has strategies top and bottom, which he plays with probability P and 1 minus P respectively. And player 2 has strategies L, C, and R, which he plays with probabilities. Well, we don't even have to assign probabilities now, we will do it later. First, there is no pure Nash equilibrium, we can just check it by direct check. So from here, player 1 would go here, from here, player 2 would go here, from here, player 1 would go here, from here, player 1 would go here. I mean, from, you don't see my mouse probably. So from TL, player 1 would go to, player 2 would go to TC, from TC, player 1 will go to BC. From TR, player 1 will go to BR. From BL, player 1 would go to TL. From BC, player 2 would go to BL or BR. Anything is better than BC. And from BR, player, is that an equilibrium? No. Player from BR, player 2 would go to BL. Yes. Okay. So there is no pure Nash equilibrium. No mistake in the numbers. Now, since every pure strategy implies that the other strategy is the best response, and that all the best responses are pure, there can be no partially pure mixed Nash equilibrium. So we are going now to look for the fully mixed equilibrium. There has to be at least one, because there has to be at least one mixed Nash equilibrium from Nash theorem. So this is a constant sum game, and that's all this idea of active and equalizing strategies for constant sum games. So we are going to look what is the max mean of player 1. So when player 2 plays L, player 1 playing top with probability P and bottom with probability 1 minus P gets 5P plus 2 times 1 minus P, which is 2 plus 3P. That's what the first player gets against strategy L of the other player. On the other hand, when player 2 plays C, the first player gets 0 times P plus 7 times 1 minus P. So 7 minus 7P. And when player 2 plays R, player 1 gets 1 times P plus 4 times 1 minus P, which is 4 minus 3P. And the worst which player 2 can inflict on player 1 is denoted by this purple or pink line, which kind of is the circumference, the upper boundary of the white area. White area does not mean anything at this point. So the purple line, I mean that I should have maybe changed the color, but it's okay. So that's the worst that player 2 can inflict on player 1, and therefore the best that player 1 can do against this worst case is this intersection. The intersection of 2 plus 3P and 4 minus 3P. So that's the same illustration, and 2 plus 3P equals to 4 minus 3P is the same as P equals to 1/3. Which by substitution lets us see that the value is 2 plus 3P. When I substitute P equals to 1/3, it's 2 plus 1, it's 3. For player 2, we can either draw linear functions in 2 variables, because player 2, I remind you, it has 3 strategies. And then we would have to do the same what we did here, but it would be in 3 dimensions, because there will be a function of 2 variables. But we can use other ways, which actually uses the statement which we proved against and the notions of active and equalizing strategies. So the way is the following. From the graph, we see that strategy C of player 2, that line, 7 minus 7P, is not equalizing. So, excuse me. It's not the best possible against this strategy, against the strategy P equals 1/3 of player 1 against the intersection. And therefore, since we know we've proven that active implies equalizing, being not equalizing implies not active. That's a contrapositive. Meaning that each max mean of player 2 looks as weight 0 to strategy center. So it's only L and R who can have some non-zero weight. So we can denote each max mean of player 2 as Q, then 0 to center, and then 1 minus Q to R. See, this is the matrix. So we have proven that despite that it is not dominated, it's still it's still not active. And now it's simpler. Now we can, for example, just solve as usual for any game, not even zero sum, or we can solve as for zero sum with this graphical looking for max mean, because we only have two places where it's not zero, so we have only one variable q here. But we also can use another option, which again uses our statement, this time directly, not as a contrapositive. So since both strategies of player 1 are active, they're both in the support, right? Because we found that p is 1/3, so 1 minus p is 2/3. They're both with positive probability. They're both equalizing, because active implies equalizing. That's what we've proven. That implies that against q, which is a max mean, against each such q, each pure strategy of player 1 being equalizing has to yield a value, which means basically that this condition holds and this condition holds. And well, each of them gives q equals to half. So since before we have found no pure and no partially pure Nash equilibrium, we now only have this one. Actually, okay, well, I'm just trying to see whether we even use the fact that we have no pure and no partially pure Nash equilibrium. I think we have not even used that. Yeah, I think we have not even used that. So we now found all that is, and all that is p, I remind you, equals to 1/3. That's what we found here. And now we have so found that q equals to half from either of those equations. And therefore make the only mixed equilibrium is 1/3 and 2/3, so p and 1 minus p. And here we have q half, 1 minus q half, and here I remind you is 0, because it's q, 0, 1 minus q. Okay, and next we are going to talk about potential games.